This chart shows a strategy optimized with 21 parameters over 25 months. The result? 3,342% profit and a Sharpe ratio above 3.0. You launch the bot. Within 2 weeks, it loses 18% of its capital. By day 30, the drawdown hits 34%. This collapse is the result of a brittle architecture. When a model is tuned to 21 different variables, it becomes so tightly coupled to the specific sequence of historical data that it cannot survive a change in market conditions. The parameters that looked perfect in the backtest didn't actually discover a persistent pattern. The algorithm simply memorized the historical noise. A single train test split provides only a single point estimate. The result depends entirely on where you draw the boundary. Shift it by a few weeks, and a massive profit can transform into a catastrophic loss. Walk-forward optimization replaces this single-point lottery with a systematic series of checks, sliding the optimization window across time to verify if the logic holds up. Systematically testing how parameters transfer to new data is the only way to distinguish a genuine trading edge from a statistical artifact. The foundational flaw of a 70-30 split is its dependency on a fixed, arbitrary boundary. Sliding the line forward by just 1 month can completely invalidate the results. In this case, the out-of-sample profit recalculates from positive 40% to negative 15%. This instability scales with the number of rules in your model, leading to the curse of dimensionality. Every parameter you add expands the search space exponentially. If each of your 21 parameters can take just 10 values, you are dealing with 10 to the 21st power in total combinations. To understand the danger of this search space, we use the Bonferroni formula, which measures the probability of a false discovery. If you test 10,000 combinations, the probability of finding a profitable result that is actually a random artifact approaches 100%. High-dimensional models do not inherently prove algorithmic edge. They often simply prove a computer's ability to extract a coincidence from a mountain of historical noise. Walk-forward optimization attempts to solve this by simulating a real trading cycle. You periodically re-optimize parameters on available data and then trade them until the next update. Structurally, every window is divided into an in-sample training period and an untouched out-of-sample testing period. In anchored walk-forward optimization, the start of the training period is locked in place. As the timeline moves, the training set grows, incorporating more history for each subsequent test. While this provides more data for optimization, it creates a risk. Older, obsolete market behaviors can dilute the patterns that are actually relevant to current conditions. Rolling walk-forward optimization uses a fixed-length window that slides across the data. This allows the model to adapt to new regimes by actively dropping old data that no longer reflects the current market. The most critical rule in either method is that the out-of-sample periods must never overlap. We evaluate the final strategy by stitching these isolated testing periods together. This concatenated equity curve represents the true expected performance of the system, because every single trade was generated using parameters that had never seen that specific data before. This process forces the strategy to prove its robustness continuously, replicating the exact pressures of a live deployment. Cryptocurrency markets present unique challenges due to violent structural regime switches, moving from trending bull markets to high-volatility sideways chop in a matter of days. Because of these shifts, anchored windows are often less reliable than rolling windows. For crypto, we generally recommend a 4 to 6 month rolling training period to focus on current volatility. However, crypto assets often suffer from data scarcity, with many altcoins having less than 3 years of liquid history. A standard rolling test on such a short history might only yield 4 or 5 windows, which isn't enough to provide a statistically significant evaluation. To solve this, we use Combinatorial Purged Cross-Validation, or CPCV. CPCV partitions data into groups and tests every possible combination. From 10 data groups, you generate 45 distinct train and test scenarios, vastly increasing the significance of results. To prevent data leakage, we apply purging and embargo gaps, removing small sections of data at boundaries where training and testing sets meet. We also filter these windows by liquidity. If the average daily volume in a specific window drops below your execution threshold, that test result must be discarded. Finally, the out-of-sample profit must include leverage funding rates. In high-leverage future strategies, these costs can often consume the entire edge of an otherwise profitable system. When data is scarce and volatile, these strict partitioning and cost adjustments are the only defense against false confidence. Once the pipeline produces an equity curve, we need a quantitative way to determine if the strategy passed. The primary metric for this is the walk-forward efficiency ratio, or WEFR. WEFR is the ratio of your out-of-sample profit to your in-sample profit. If the WEFR drops below 0.5, it means the strategy lost more than half its effectiveness when moving to new data. We consider any value below this threshold as a signal of overfitting. A low ratio confirms that the parameters were fitted to specific historical quirks rather than a persistent market edge. We must also track the degradation rate. This is the slope of the profit over time. If the performance in the testing window drops off sharply, it tells us how quickly the optimal parameters become stale. A high degradation rate suggests you need more frequent reoptimization or a more fundamental overhaul of the strategy logic. We can now return to that initial 21-parameter strategy. To see if it's truly viable, we run it through a final production audit. The first requirement is the trade-to-parameter ratio. Statistical confidence requires at least 10 out-of-sample trades per parameter. For our 21-parameter model, the pipeline must produce at least 210 out-of-sample trades. We verify the efficiency ratio stays above 0.5 and that optimal parameters remain stable, not jumping violently between reoptimizations. The final safeguard is Monte Carlo bootstrapping, which we apply to the aggregate out-of-sample returns. We shuffle the trade sequences thousands of times. If the bottom 5th percentile of those results is still profitable, the strategy passes. A beautiful, flawless backtest curve is easy to engineer, but it offers absolutely no protection in a live market. Only strategies that maintain efficiency across multiple, non-overlapping testing windows are genuinely worthy of live capital. Everything else is just curve fitting.